All right, AP Calculus. We just introduced the idea of continuity and is specifically thinking about describing continuity using the definition of continuity. And we were doing that through like looking at graphs and different things like that. Well, of course, just like limits, a lot of the times we're not going to be given a graph. We're going to have to be able to determine continuity algebraically. And so that's what we're going to do in our notes for today. If we're looking at example 4, we'll go ahead and get started right away. It says if the function f is continuous, and if f of x is like this function here, what is f of negative 2? All right, and so you might think, well, hey, normally, right, when we're trying to evaluate, just like the function value, we're going to plug negative 2 in, and so when I do f of negative 2, you get negative 2 squared minus 4 over negative 2 plus 2. And when I evaluate the numerator and the denominator, I end up getting 0 over 0. And of course, when we have 0 over 0, that's called indeterminate form. And while we're, the 0 in the numerator doesn't really matter to us, the biggest problem is that we are dividing by a 0, which we have seen a ton when we are evaluating limits algebraically. We know that that is not okay. And so, where do we go next? When we're reading this problem, that's really the only information they gave us until you recognize that this is AP Calc, and a lot of times they will pack a lot of information in one key word or phrase. And the fact that they tell us that our function f is continuous tells us a lot about what's happening. Based on the definition of continuity, which we talked about the other day, if a function is continuous, that means that the limit, as x approaches, in this case, will focus on negative 2 of this function. That is equal to the function value at that x value. So the limit as x approaches negative 2 of f of x is equal to f of negative 2. And that hits on every single piece of our definition of continuity. Again, the first part is that the limit exists. The second part is that the function value exists. And the third part is that they are equal to each other, and that is when we know that the function is continuous at that x value. And so we can actually use this information in order to help us find f of negative 2. We need to figure out what the limit as x approaches negative 2 of this function is. And when we were talking the other day, last week or so, when we ended up trying to evaluate the limit, we would first try direct substitution. And we just did that and it didn't work. We were dividing by 0. Next step is to factor. And so when I'm factoring this, I have a difference of squares in my numerator. So I get x plus 2 times x minus 2, all divided by x plus 2. And what do I notice is happening? We have a factor in our numerator, canceling with a factor in our denominator. The reason something weird was happening when we tried direct substitution was because we're evaluating the limit at a whole, which means that we can now go back to direct substitution. As we've talked about, you're familiar with this, with our simplified function, and we'll be able to find the limit as x approaches negative 2. When I do that direct substitution, I get the limit is equal to negative 4, and because of the definition of continuity, which we have written over here in green on the left, we now know that f of negative 2 is equal to negative 4. So we have found that function value. All right, let's try another example. This one's going to be slightly different. For example 5 that you see here, we have a piecewise function, and we have a constant c in both pieces. We need to figure out what that constant c needs to be in order to make this function continuous over all the real numbers. Now, because we're AP Calculus, we can't just see a problem and start to do the math. We actually need to consider what's really happening here. And so when I'm looking at this piecewise function, right, I notice that this first piece, that's just a line, right? And it's in slope-intercept form. The second piece is going to be a quadratic, a parabola. We know that nothing crazy happens with either of those functions. Those are both polynomials, and we'll even, when we get to this third example, and we're looking at this piece down here, this cubic, right? All polynomials are continuous over all reals, over all numbers. You don't have any holes. You don't have any vertical asymptotes. There's nothing fancy or like crazy going on over the course of these pieces. And so the only issue that we could come across when we were talking about continuity for this piecewise function is where the split occurs at 3. What I mean by that is, like, let's just, hypothetically, I don't know what this graph looks like perfectly, but let's say we have some line. And then we also have a parabola. Right, this split, because of our piecewise function, opens up the possibility for a jump discontinuity to occur. And we talked about that vocabulary the other day. A jump discontinuity is when you have what we see here. We are jumping from one piece to the next, and there's this gap between our functions. We are saying, hey, we need the value c to make sure that this function does not have a jump discontinuity. That something like this is happening here, where we can trace our entire function, both pieces, our line and our quadratic, and we don't have to pick up our finger or our pencil. And we're going to do that, of course, by thinking about the definition of continuity. We always come back to that definition of continuity. Definition tells us that the limit as x approaches 3 of g of x needs to equal the function value. Well, in order for us to determine what the limit is, we need to know what the one-sided limits are. So the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. And if this is continuous, these one-sided limits need to be equal to each other. Now, we've talked about this before, but when we are trying to decide what piece of our piecewise to use, for example, when we're trying to evaluate the limit as x approaches 3 from the left, that means we're looking for what piece of our piecewise is defined for x values that are just to the left of 3, that are less than 3. And that's going to be this top piece of our piecewise, cx plus 1. In the same way, the limit as x approaches 3 from the right, we're looking for the piece of our piecewise that is defined for x values that are just to the right or just greater than positive 3, which is going to be this piece that is our quadratic. And so from here, we can use direct substitution to come up with our left and right pieces. After using that direct substitution, plugging in 3 for x in both of these limits, I get 3c plus 1 for my left-sided limit and 9c minus 1 for my right-sided limit. Again, in order for my two-sided limit to exist, which is true if this is continuous, that means that my one-sided limits have to be equal to each other. Yay, equals. What that means for me is that I can set 3c plus 1 equal to 9c minus 1, and now I have an equation that I can solve in order to get my c value that's going to make this true, that's going to make it continuous. I'm going to go ahead and move my c's over to one side, so I'm going to subtract 3c on both sides, so I get 1 equals 6c minus 1. Move the 1 over to the other side, and I end up getting a c value of 2 over 6, which reduces to 1/3. And this is the value for c that will make this function continuous, that will make sure that there's no jump discontinuity between my pieces. And we can go ahead and double check to make sure that that's actually true. I plugged in 1/3 for c into both of these left and right sided limits, and I did that in purple. You'll see that I actually do end up getting both of my limits are equal to 2, which checks off the first piece of our definition. And then when we're considering like, hey, let's think about what g of 3 is equal to, we're going to come back to our piecewise, and that's where this, or equal to, x is less than or equal to 3, so that when x is 3, which is what we're looking for, g of 3, I'm just plugging it into this top piece, which we've already done. We found it was 2. Yay, we are all good to go. And this is super, super common on AP for you to find this value, this constant, that will make your piecewise function continuous over all the real values. Okay, let's try one last example before we finish up. We have a piecewise, and it says, hey, for what values of x is h of x not continuous? Again, before I actually get into doing any work, I just want to think about what I'm dealing with here. Well, if I'm looking at this piecewise, again, this first part, negative 2x minus 5, That's the equation of a line. No discontinuities there. This second piece is also a line. It's actually a horizontal line. Y equals 3. No discontinuities. And lastly, this polynomial, this cubic, also we know has no issues with continuity. And so the biggest issue we are worried about is at an x value of -2. There's a chance, because of jump discontinuities or holes or whatever, that at x equals -2, like that would be the only value potentially where h of x is not continuous, so that's where we are going to focus. Well, again, let's start from the definition of continuity. In order for this function to be continuous, the limit as x approaches -2 needs to exist. And in order for that to exist, we need to break it up into our left and right-sided limits. When we are considering our limits from the left, just like we did in the last example, I want you to tell me which piece of my piecewise am I focused on for my left-sided limit. Well, the piece -2x minus 5 is defined for x values that are less than or to the left of -2. Beautiful. And when we do our direct substitution, plugging in that -2 in for x, we're going to get a y value, or a limit value of -1. Now I want you to tell me what piece we're using for the right-sided limit. Beautiful. I hope you're able to pick out the piece, the cubic, because that is defined for x values that are greater than or just to the right of -2. And I already went ahead and did that direct substitution, and when I evaluate this limit, I end up getting a y value of 7. And so immediately, right, in order for this to be continuous at x equals -2, my one-sided limits have to be equal to each other. In this case, we have a -1, we have a 7. They are not equal to each other, which means the two-sided limit doesn't exist. Already, that first piece of the definition of continuity does not hold true at x equals -2. And so, like, we're going to stop there. But the biggest part of AP, like I've mentioned multiple times before already, is this piece where they say justify. Again, it's just one word that is loaded. There is a lot of expectations for you when they say this word justify. And so because we are going to be in AP, we need to make sure that we are doing a proper, nice justification. And that means we're going to have to write a little bit. And so I'm going to start by saying, hey, the limit as x approaches -2 of this function h of x, it does not exist. Notice how I didn't say it does not exist. I was very specific. The limit as x approaches -2 of h of x does not exist. We'll talk about this more in class, but you need to be as specific as you possibly can be with AP. No writing the word it. You need to tell me what does not exist. The limit as x approaches -2 of h of x does not exist because I need to tell you why, right? I need to argue and prove to you that I know why this doesn't exist, because the limit as x approaches -2 from the left of h of x does not equal the limit as x approaches -2 from the right of h of x. So, you could also do those three dots, right? For therefore, h of x is not continuous at an x value of -2. When I'm looking at this justification, you could write this in a few different ways, right? I could have said h of x is not continuous at x equals -2 because the limit as x approaches -2 from the left is not equal to the limit as x approaches -2 from the right, so therefore the two-sided limit does not exist. Like, you can move these pieces around, but it is vital that you say the what, right? I don't just say it. I want to say h of x. That is the function we're working with. I need to say, is it continuous or is it not? I need to be specific about the x value that I'm talking about. I can't just say h of x is not continuous because this. I need to say, where is it not continuous? And I've included that piece here. And then your big, massive justification, which is going to be very notation heavy, but it is very important. And like, this is the biggest piece of your work for AP. And again, we're not just testing you on math. We're testing you on being able to come up with an argument. Like, once you decide on an answer, tell me why it's true. How do you know? You need to prove it to me. Just to stamp what we were seeing, I went ahead and graphed this piecewise function. We see, yes, just like we determined, as we approach from the left, we're getting towards a y value of -1. As we approach -2 from the right, we're getting towards a y value of 7. There is a massive jump discontinuity here. This function is not continuous. All right, we'll see you in class so we can practice more. Let's go AP Calc. Woohoo!